A large language model doesn't act alone. It operates inside a harness, a non-parametric shell made up of system prompts, tools, memory states, and runtime policies that connect the fixed model weights to an environment. The bottleneck in building these systems is that harness design is highly model-specific. A scaffolding structure optimized for one model's habits, like Qwen 3.5, will often cause a completely different model, like GLM5, to fail. The friction comes from trying to force distinct behavioral patterns through the exact same execution rules. Historically, engineers solved this manually. They wrote custom React prompts by hand, or they used a stronger, more expensive supervisor model to guide a weaker one. But foundation models are releasing at an accelerating rate, and their architectures are becoming increasingly diverse. Human tuning and external supervision simply cannot scale to meet the demand of every new release. This brings us to the self-harness architecture. Instead of relying on humans or external supervisors, an agent improves its own operating harness by analyzing its execution errors and rewriting its own code-level scaffolding. To scale autonomous agents, we have to bypass external bottlenecks entirely and allow the models to author their own environments. The self-harness architecture relies on a three-stage optimization loop, starting with weakness mining. First, the fixed base model is run against a specific, held-in set of training tasks to generate a batch of execution traces. This produces a raw, chaotic dataset of successful task trajectories scattered alongside the failures. If the system treated every failed task as an isolated anecdote, it would chase phantom bugs. It needs to find recurring patterns through trace clustering. It groups failures using a strict signature equation. A cluster forms only if traces share the exact terminal cause, agent behavior, and mechanism. This ignores superficial symptoms, isolating deep structural weaknesses and compressing them into a structured evidence bundle. Weakness mining acts as the essential translator. It converts noisy task failures into targeted engineering objectives that the system can actually address. Once the evidence is collected, the system moves to the harness proposal stage, invoking the exact same fixed base model to act as the proposing engineer. The proposer operates inside a heavily bounded context, receiving the mined evidence bundles and accessing only specific, editable surfaces of the current harness. The model cannot rewrite its core architecture from scratch. Its generated proposals must target a specific failure mechanism with a precise, minimal edit. But unconstrained self-improvement is dangerous. An agent could easily overfit, writing rules that solve past mistakes while breaking future tasks. That is why the third stage is proposal validation. Every candidate edit is a distinct variant. It must pass regression tests on both original held-in training tasks and completely new, unseen held-out tasks. The acceptance equation demands measurable progress. An edit is merged only if it increases the pass rate on one split without degrading the other. If a new rule patches a bug but drops performance on an unseen task, it is strictly rejected. This zero degradation regression gate forces the agent to learn generalized workflow optimizations. It prevents the model from simply memorizing the test set. We can see exactly how this operates empirically by watching the Qwen 3.5 model attempt the extract ELF task on the Terminal Bench 2.0 environment. Under the baseline harness, Qwen falls into a cognitive trap. The trace shows it encountering file overwrite friction. Instead of adapting, it endlessly retries the same ineffective command, eventually deleting the required artifact before the verifier can check it. Without any human intervention, the weakness mining stage analyzed these traces and identified the specific vulnerability in the agent's recovery logic. The proposer then authored and validated a targeted code-level intervention, a tool error-triggered artifact prompt middleware. When we look at the execution trace under this newly evolved harness, the behavior shifts completely. Upon hitting an error, the system prompt intercepts the failure and actively redirects the agent to recreate the missing artifact. The death loop is cleanly broken. The algorithm identified a model-specific failure mode and authored a permanent structural code fix to prevent it, operating entirely autonomously. This chart shows the pass rates on Terminal Bench 2.0 across three fundamentally different model families, comparing the initial baseline harness to the evolved self-harness. Notice the uniform performance gains specifically on the held-out task splits for MiniMax M2.5, Qwen 3.5, and GLM5. Because these tasks were entirely unseen during the proposal stage, these gains prove the system is generating reusable, generalized workflow logic, not memorized answers. And the solutions were highly bespoke. What worked for Quen was completely different from what the other models required. For MiniMax, the system discovered it needed an intervention to strictly bound its tool use loops to avoid stalling. GLM5, meanwhile, required an entirely different structural edit, focused on creating persistent environment pathings across shell sessions. These results suggest that we can reduce our dependence on manual engineering or external supervisor models. It offers a scalable way to adapt a common harness to the specific failure modes of a new foundation model. By grounding the self-improvement loop in empirical evidence and strict regression gates, agents can autonomously identify and correct the specific code-level weaknesses in their own operating harness.